Okay, so it is a pleasure to have Lori Ziegelmeier today, and she will tell us about minimal cycle representatives in persistent homology using linear programming.
Okay, great. Thank you, everyone. It's nice to see you all virtually. So I'll begin with a bit of motivation for this. So imagine that we have some data and it's realized in some sort of topological space. And what we would like to do is understand the structure of this topological space, perhaps by understanding the holes that are within the data. So we could potentially find a cycle representative of a homology class. Now, cycle representatives are not unique, but they tell us about the various holes that are enclosed. In this talk, I'll try to use the term cycle representative instead of generator, because generator has been used in different contexts a few different ways, but if I do accidentally say generator, I mean cycle representative. Okay, so here's one cycle representative enclosing that hole. Now, here's a different cycle representative of a different homology class. And you might say, well, that one seems more complicated somehow. But, you know, it's a perfectly good cycle representative. So the idea is that various cycle representatives can sort of create ambiguity and lead to many different interpretations of the same set of homology classes. So for instance, perhaps you might like this cycle representative better. It seems more geometrically concise, so perhaps that is to some benefit. And so we often want to know information not only about the existence of a homology class, but also information about the location and the shape of the hole that the homology class has detected. Okay, so the plan for this talk is that I'll spend some time doing some background, and then we'll talk about why we might want some tight representatives. And then I'll describe a comprehensive empirical study that I did with my collaborators where we investigate all sorts of properties about cycle representatives. So before I go any further, I'd like to mention my collaborators. So I worked on this project with Lou Lee and Connor Thompson, as well as Greg and Chad. And so Lou and Connor were undergraduate students at Macalester, and Lou in particular had never taken topology before starting this project, and within a year she had this paper published. So I think that is really remarkable. So you can find our paper here, and then we have code libraries also available on GitHub. So the underlying ideas behind our paper really stemmed from two other papers by Obayashi and Escolar and Hiraka. And these are methods for optimizing cycle representatives to have some geometrically concise behavior. I've also got a couple of papers up here that are sort of under the umbrella of something that we're calling exact. So exact is a platform that Greg, Chad, and I are developing along with our postdoc Haiben Hung and other undergraduate students and so on. But the idea is that exact is a platform that lets people do calculations that they can't already do by giving a nice, clean way to get access to and work with sparse matrices. And so like computing, I almost said generators, computing cycle representatives is sort of a basic first step. And this minimal cycle representative idea can show you how you can use some of these tools. Now, we also have this paper that's come, so I should say that this paper describes some factorization schemes to nicely work with these sparse matrices. And this paper is a nice overview of the relationship between cycle representatives and matrices and so on. And we give a nice framework to be able to understand these things. Okay. So I'm sure most people here know homology, but I want this to be a standalone talk, so I will give a super quick overview here. What is homology? Basically, it's finding loops in a topological space. So if we have a CW complex, which is a two-sphere, we can think of this as a union of points, lines, disks, and balls. And what we want to do is be able to describe the structure of this topological space. And so we can define this function, which is an alternating sum relating the sum of a cell to its boundary elements. And we can put that information and encode it into a boundary matrix, where the boundary matrix relates, say, the 1 cells to the 0 cells, the 2 cells to the 1 cells, and so on. And from this boundary matrix, we can compute some important spaces. So we can compute the image of the boundary and the kernel. And we know since the image is contained inside the kernel, then we can do some neat things. So often we call the image the K boundaries, and we can think of these, the kernel as the K cycles. And then homology is just looking for those cycles which are not boundaries of K+1 chain. And so homology can uncover various cosets. We can take this quotient here, and we can get a cycle we can think of the quotient as revealing the homological information. Okay. So then we want to move on to persistent homology. And the idea is if we aren't given a nice topological space, but maybe a discrete set of points, how could we build a nice topological space and understand the topology of it? So maybe you're given this point cloud, you see this, but really you construe this. And if you want to tell a computer something, you might fill in these points with a union of balls. Okay. Now, in persistent homology, we do this with choices of scale parameter of various radii, and we see that we have different structures at different scales. Now, we can take this space and get a nested sequence of topological spaces indexed through this filtration by this scale parameter. Now, what I want to do is sort of take this data-centric approach and then look at more of an idealized model. So here, let's take our different topological spaces. And we can have x0, x1, x2, and x3. Now, the idea is that imagine we want to uncover cycle representatives. So if we have this cycle representative A, what that really means is that at the filtration value corresponding to this topological space, we have an element in the homology class. So there is a cycle representative that you can think of as this coset representing the homology class here. Okay, and we see that this list lives for a while through the next topological space, and then it eventually dies at x3. So we record that information in an interval or a lifespan of A, where the cycle appears, and then once the cycle becomes homologous to 0, then the cycle vanishes. And we can think of the interval decomposition of this, or the interval representing this cycle representative as the index when it first appears and the index when it no longer remains. So normally we are, or a lot of times in our analyses, we first start with recording this interval decomposition of our topological space. We can do this for both of the cycle representatives, and we call this a barcode. And of course, we can extend beyond this idealized model to instead consider a nested sequence of spaces. Now, what we want to do is, oh, and I should say, it's common that we often say, since A is longer, the lifespan of A is longer, it's more robust in some sense. Okay, so what we want to do is go beyond the barcode and really understand not just the length of a feature and how long it persists, but rather what is that or something geometric about that various feature. And so we want to dive into cycle representatives. Okay. So have a question here for you. If you have two cycle representatives of two different homology classes A and B, which one might you prefer? There's no right or wrong answer, but yeah.
B.
You like B?
I say B.
Okay. Yeah. Maybe you like A because you just like complicated things. It totally depends on your application, right? So the idea is if you want some notion of a good cycle representative, it might depend on your application. So for instance, maybe you want to locate a feature in some data. And what this means is maybe coming up with a nice concise geometric measure to represent that cycle representative. Maybe you want to visualize this, or maybe you prefer nice smooth curves or something, or the geometry matters. Okay. I've got just a couple of examples here of some applications of when you might want a nice concise geometric measure of a cycle representative. So Wu and collaborators explored 3D reconstruction of cardiac trabeculae restoration. So these are complex muscle structures. And the idea is they wanted to use topological priors and cycle representatives to try to segment these objects. And when they started originally, they just found cycle representatives, but they could be really convoluted and messy. So it didn't allow for good segmentation. However, here, after they found a more tight cycle representative, then they got much better segmentation. This other example by Emmett and collaborators, they explored chromatin interaction to study folding. So these are three-dimensional structures of DNA in the nucleus. And different loops represent different types of chromatin. And so they needed to be able to have concise geometric notions here. Okay. So what might make a cycle representative good? Well, it's up to the modeler to make that decision. So one notion of good could be tightness. So how tight does a representative enclose a hole? Another might be a connection to graph theory when you want just a simple closed curve. So you don't want loops, multiple loops representing a single cycle here. Okay. And so these are the idealized models. If we look at some data here, of these three annuli together, here was an original cycle representative. It's much more complicated. Whereas here is a more concise geometric measure. So depending on your application, you might prefer this to be able to understand what's going on with this cycle representative better than this one. Okay. And now I'm going to go through an example filtration just to make sure that we fully have a nice picture in mind. And I should have said back on the collaborator page that my collaborators made a lot of these beautiful slides. And in particular, you'll see some beautiful slides that Lou made. She's now a grad student at Penn State. And I forgot to mention that Connor is a grad student at Purdue. Okay, so of course, this is the Vietoris-Rips seminar. So we're going to use a Vietoris-Rips filtration on this sample point cloud. We can think of growing some balls, and once these balls start intersecting, we can start adding simplices. So we can, at this scale parameter, we can add two different edges, AC and CB, or BC. And then add another scale parameter, we can add some more edges, and we keep growing. Oh, I should say once the three edges of, are formed here, then we can consider the two simplex that's added in there, and then add some more edges. And then at the moment when we have this final edge created here, that's when we have a cycle. So at the birth of this one simplex, we have a cycle that's formed. Okay, and so this cycle, we could think of it this way, or analogously, we could go along AB. Those would be two cycle representatives. Then we can keep adding edges on the interior of the cycle, and we're sort of shrinking the area of the cycle here, and we can keep going. And then at the moment when we add this final edge, then we're actually adding two simplices. And these two simplices now fill in the cycle. And so the birth of these two simplices means that we have the death of a cycle. Okay, so we can make a choice and say, okay, this is the simplex that was born at the death time of this. Now, often what we do is think of a simplex-wise filtration where we order elements by, say, dimension first, and then filtration value, and then maybe we have some alphabetical order for this. And the key thing is that we have a birth one simplex, and when our two simplex is born, then this cycle dies. Okay, so now we're ready to get on to some minimal cycle representatives. So the pipeline is as follows. Imagine you have some point cloud, you consider a filtration on it, we get a barcode, and then we want to dive into the barcode and really understand cycle representatives. So we'll look for a representative for a single bar. And whatever our persistence algorithm spits out, that will be our original cycle representative, and we'll call that XORG. Okay, now sometimes we're going to be optimizing XORG explicitly, and sometimes we're going to be optimizing the area that XORG encloses. Okay, so we're going to consider how to minimize a persistent cycle representative. And there's lots of other approaches out there. So Wu, Chen, Day, a bunch of other collaborators and people have worked on this using A-star heuristics or Dijkstra's algorithm, or fitting a cycle representative within a ball of minimum radius. But the approach that we're going to focus on uses linear programming because it's simple and flexible and can give us some interesting results. So the idea is we can start with an original cycle representative, and what we want it to do is be a persistent cycle representative. So that means we want it to have this, the optimal cycle X, we want it to have the same birth and death time as this original cycle according to some loss function. And what do I mean by a loss function? Well, we're going to restrict ourselves to dimension one. Everything we do in our paper can be any dimension, but we're going to just focus on dimension one since it's most straightforward. And so what we mean by loss is a way to measure the size of our cycle representative. And so how do you define that via linear programming? We're going to consider 4 different approaches. We're going to try to minimize the number of edges that a one cycle includes, the weighted length, the number of triangles that a one cycle bounds, and the weighted area. Okay, and then as I mentioned, those two papers that I highlighted earlier, the Escalar and Hiraka one focuses on the one cycles. So these we call edge loss methods. So it minimizes the number of edges or the length. And the Obayashi paper focuses on minimizing the number of triangles or the area. And we've made some modifications to both of these papers in our analyses, but I'll try to highlight some of the modifications. Okay, so the first one is that we want to minimize our number of edges. So we can think of this in terms of using the zero norm, which the zero norm of a vector just takes the number of non-zero entries. So for instance, if we were given this original cycle, we could encode it as a vector of ones, negative ones, and zeros, where we say include this simplex or don't include this simplex, or negative says include this simplex but reverse the orientation. And what we do is we say, okay, take our original cycle and then add some boundaries. Now, in an early paper by Day, this is what they considered. They wanted to find homologous cycle representatives. But in the Escalar and Hiraka paper, they wanted to sort of factor out redundant information to get a cycle basis. And so they included, we can also add to this cycles that are born before X original. Now, if you do that, you could actually have cycles then that die after X original, so you don't end up with a persistent homological cycle basis. So we add that constraint that it also needs to die before X original. So the idea is we can take this cycle representative and we can add some boundaries or cycles that are born and die before X original. And if we, for instance, add the boundary of ABC here, then we can get a new cycle representative. And we see that we went from 7 edges down to 6. Okay. Now, it turns out when you're trying to minimize things, the zero norm is NP hard to minimize. And so, but it's highly interpretable. So if you have a vector and you can count the number of non-zero entries, particularly if those entries are 0, 1, or -1, then it's easy to interpret this. But we actually want to be able to compute this minimization problem. So instead, we replace the 0 norm with the 1 norm, which is known to promote sparsity patterns. And so we could introduce the 1 norm and approximate that, say this is approximately the number of edges. Another constraint that you could do is you could add that you want X to be integral or not. So if X is integral and we have the 1 norm, then it becomes slightly more interpretable, particularly if those solutions are 0, 1, and -1. And in that case, then the 0 norm and the 1 norm solution would be identical. Okay. So, and I do want to say that Day has given some theoretical properties to see when a linear programming problem, or if you add this integral constraint, that might be called a mixed integer program, to see when these two things will give the same solutions. It doesn't happen frequently in practice, but as we'll see, these cycle representatives actually have surprisingly nice behavior. Okay. So we also are going to consider weighting this by the length. So in a Viator-Rips complex, we have some notion of distance. So we can use that notion of distance to weight each simplex. And then, of course, we can consider this X integral or not. And with weight, or with this weighting, we're just considering the length. So an optimal cycle representative would be have the smallest length here. So that's two different optimizations, minimize the number of edges, minimize the length of a cycle. Now we're going to move on to some triangle approaches. So here we're going to take V, which we can think of as a volume, or in our case, since we're considering one cycles, an area that is enclosed by our cycle representative. So we're going to consider X, the solution will be the boundary of this volume. So you can think of it as the boundary of this two chain. Now, what we're going to do is, again, try to minimize the number of triangles that a cycle bounds. And we're going to have the restriction that we want that V must include the triangle born at the death time. And then it could include some other triangles born during the lifetime of X. It also must include the edge that's born at the birth time, but it can't include any edges that are born after that. So let's go back to our example here with our simplex-wise filtration. And that's a key point of this algorithm, that we need to have the simplex-wise filtration. And so in our software, we have a nice framework for starting from a Vietoris-Rips complex and being able to do this. So the idea is we need to first start with the death simplex. So the simplex born at the death time. So we can start this. Now we have two edges that are not allowed, because you cannot have these edges that are born after the birth simplex, which was born up here. Okay, so we can start adding triangles until we no longer, now we see we only have CE is the only edge that's no longer allowed. Okay, so we can keep adding triangles. Now CD is no longer allowed, and we can keep adding triangles. And now we have something important. We have the edge that was born at the birth time. We have the triangle that was born at the death time, and we have no edges that were born after the birth time of the original edge. So this is now a valid cycle representative for this homology class. Okay. Okay. So yeah, this is now valid. Yay, good. And just like with the edge loss case, we can, instead of using the 0 norm, we can replace this with the 1 norm and consider if V is integral or not. One other important thing to point out is that an original cycle representative is not needed anywhere in this. We just need to have this simplex-wise filtration and be able to say, okay, what's the death simplex, what's the birth simplex, and then proceed from there. Okay. Now, something else to keep in mind is that these are different notions of minimization, so you can get different cycle representatives. So the edge loss method has fewer edges, but it has more triangles. And the triangle loss method has more edges, but it has fewer triangles. Okay. And then finally, we can also weight each simplex by an area. Now this is kind of complicated. If you you can use Heron's formula to find the area of a 2 simplex. So we can think, I guess this is not complicated. Later on, there's something complicated I'll try to point out. So we can use Heron's formula to find the area of a 2 simplex, which can then give us a weighting on all of these triangles. Okay. I wanted to just say a quick note about linear programming. So linear programs are of this form here. while mixed integer programs are of this form, where we have a constraint that at least some of our decision variables are integer. Now, all of the problems that I've discussed here can be written in this form, where we take a one norm, which has an absolute value. So you have to do some magic where you replace your decision variables in a special way to account for that absolute value. But you can consider the decision variables. They're either one chains if they are in the edge loss case, two chains if they're in the triangle loss case, or an integral or not. Okay. Now, a linear program, you can think of it as fewer constraints. It's a nice convex optimization problem. There's methods to be able to solve this. The simplex method, which is exponential, but it often runs super fast, or there's polynomial time interior point methods. Mixed integer programs, there's some linear programming relaxations you can do and some approximations, but there's like no like clear-cut way to solve these mixed integer programs. So whenever we add that integer constraint, think of this as a much harder problem.
Lori?
Yes.
How many more pages do you have? You have 5 or 6 minutes, I guess.
Oh, okay. I have quite a few pages, but I anticipated that. So
Okay.
yeah, please feel free to stop me whenever you want me to stop. Okay. Okay. So in summary, the idea is that we have 4 objective functions, 2 for edge loss, 2 for triangle loss, and then we add the constraint that something is integral or not. Okay, and so there's 8 optimization problems that we're considering here. Now, before we get into some of the details of our analyses, here's just a simple example. Here's an original cycle representative, and then here are 4 solutions to 4 different optimization problems given in green. Here we have various loss functions. So think of this as the number of edges, the number of triangles, the length and the area. And we see that each representative actually does optimize the thing it sets out to optimize. Okay, so perhaps these, maybe this one seems natural to be the one that encloses the smallest amount of area. This one encloses the smallest amount of edges. So these different notions give you very different cycle representatives. So it certainly depends on the modeler to choose these choices. One other thing I want to point out is that these can use the actual zero norm, because once we have a solution, then we just say, okay, what are the non-zero entries there? Another thing to point out is that the solutions to this unweighted problem are often non-unique. So for instance, this solution could alternatively have worked for this uniformly weighted optimization. So either of those would have been possible. One final thing before I get into results is that both of these methods optimize a single cycle representative at a time. Now, if you wanted an optimized persistent homology cycle basis, unfortunately, this doesn't quite give you that. There's a couple of choices. One, the simplex-wise filtration for the triangle loss method, and 2, for the edge loss method, we had to start with a persistent homology cycle basis to optimize. And so you don't actually get a completely optimized persistent homology cycle basis, but you get a persistent homology cycle basis where each cycle is optimized. So that's just one point to pay attention to. Okay, so what we were interested in understanding is an analysis of various cycle representatives. We want to understand what happens when we optimize these. So maybe we want to relate to the computational cost, We want to see how much does an original cycle representative shrink when it's minimized, and then what is the structure of the input and output. So we constructed several experiments of various data sets to explore all of the cycle representatives of these. So we looked at Nina Otter's and collaborators' roadmap paper and took their data sets, which have a variety of distance notions on this. We also created 360 point clouds of various dimensions and distributions using Euclidean distance. And then we did the Erdős-Rényi random point clouds by using a probability measure to make connections between graph vertices. Then we wanted to do computation on this. A few things to point out. If you want to do minimization on, say, Z2 coefficients, that's an NP hard problem. So what we actually needed was a novel solver for persistence with rational coefficients. So that's part of our software library. And then we need to be able to work flexibly with the boundary matrix, taking portions of a boundary matrix and so on. So that really highlights some of the need for software like Exact to be able to flexibly work with a boundary matrix in a nice way. And then, of course, we formatted inputs to linear solvers, and then we used two commercial solvers to do the minimization, Garabi and GLPK, but they are free for academic users. Okay, so here's what I have lots of experimental results, but my plan was just to sort of highlight the main takeaways, and then we can go back and I can talk about any in more detail. Does that sound like a good plan? 3 minutes?
Okay.
Okay.
3 minutes.
Okay. So we did a whole bunch of comparisons on the timing, and some takeaways is that the optimization actually takes longer than the persistence, which perhaps is a bit surprising in a lot of the cases. The solver matters a lot. We used the Garabi solver because the timing, which was much less for most of our experiments after doing this initial experiment. Something else that is important to consider is that most of the triangle loss problems took longer than the edge loss problems, and this should make sense because you're working with the matrix of 2 simplices to 1 simplices instead of 1 simplices to 0 simplices, and so it's a larger matrix. Now, this is not always the case if you have an interval of shorter persistence, because then you're working with a smaller portion of the boundary matrix. Something else to consider is that always the integer programs took longer than the non-integer programs. This is not surprising, but what is surprising is that these are actually on the same order of magnitude. And essentially, if you look at the ratio of these, most of the time they have this about the same time to minimize the integer program as the non-integer program. The only time where it's very different is when the linear programming problem solves super fast. But both of these give pretty consistent results. So if we think of these as the solutions to all of these, they are similar a lot of the time. And the cost, the output of the objective function is essentially the same. So you can use either method or the non-integer program to speed up computations. If we consider the average size, we looked at an experiment here where we look at various original cycle representatives, and we look at the size breakdown for distributions and dimensions. And it turns out that most cycles start small. So you can check that out more if you want. If we look at the effectiveness of optimization, it turns out that the various approaches do in fact do some more compression, but as might be assumed, the smaller a cycle starts out, there's less that can be optimized. So larger cycles can be optimized more, and that should be pretty natural. Okay. I think I will skip this. It turns out that the length, minimizing length, does not necessarily minimize area, but sometimes it does. And minimizing area, you can actually have a larger cycle than when you minimize by length. It's a little complicated. I'd be happy to talk more about it in the questions if people have any questions about this. And here's a little example. If we look at original loops of a cycle representative, it turns out that for standard distributions, original cycle representatives are not very loopy. So they usually, the support is usually just one loop. But we get qualitatively different behavior than the Erdős-Rényi random complexes. So in the Erdős-Rényi random complexes, you could have up to 17 loops, which is interesting. And so this actually relates to some work by Kale and collaborators that Erdős-Rényi random complexes actually look and feel very different than data found in nature. Okay, and this illustrates that point. And then probably the most exciting, surprising part of this is if we look at the coefficients of our solutions, it turns out, as we mentioned, we would like 0, 1, or -1 coefficients, but it's hard to guarantee that with an L1 optimization problem, but an L0 problem is computationally intractable. So what's amazing is when we found all of the cycle representatives, the unoptimized cycle representatives, most of them already had these nice coefficients. And basically everyone, once you optimize, you could get these nice coefficients. That's true for the real world and synthetic data sets. It's not true for the Erdős-Rényi data sets, which actually makes sense because we would expect some projective planes and some more non-orientable structure. So we would expect that these coefficients might not all be 0, 1, or -1. So the amazing thing is that you can actually drop integral constraints and still achieve an integral solution for all of these. I think there were something like 40,000 cycle representatives that we considered in these data. So just a quick overview is that cycle representatives, even unoptimized cycle representatives, behave really nicely, maybe surprisingly so. If you want to optimize, then you can get a more geometric, concise representation. And it turns out that you can actually consider faster problems and really do a linear relaxation to solve these L0 problems. Okay. Now, next step might be, why are these things true? And that is probably pretty complicated to figure out. So I'll just close by highlighting my collaborators again. And I also want to mention one other Macalester student who has taken some original code that we wrote in Julia and connected it now to the exact platform in Rust. So, thank you.
Thank you. And let's unmute ourselves and thank Lori for the wonderful talk. Any questions?
Lori, could you explain the slide? Most cycles start small.
Most cycles start small. Most cycles start. Oh yeah, this one. So this is an experiment where we took all of the 360 different point clouds of different distributions and dimensions, and we just looked at the original cycle structure. So the number of edges within that. And we see that the vast majority of those had 5 or fewer edges in the original cycle representative.
Okay, I see. Meaning that like if most cycles start small, then for those cycles, there might not be as much room for improvement as for the other cycles.
Yeah. Yeah,
And
and
then-
so this is, this is just looking at what was spit out by the persistence algorithm without doing any optimization.
And then another question. So, if I don't know exactly which optimization problem I want to solve, but I want nice cycles, is there one algorithm that you would start with?
Yeah, that's a good question. Let me see if I can. That's highlighted a little bit in this slide. So first off, I wouldn't bother with the integral constraints. We saw that the integral constraints, you really can solve the linear relaxation to get more what you want. Now, it turns out that if you take length minimal cycles, they're actually also uniform minimal most of the time. And similar, but area minimal could actually have, let me say this right. But area optimal cycles may not actually enclose the smallest bounding area. So this is a little weird, but remember that constraint that you have to include the depth simplex in a volume or triangle loss problem. So because you have to include that depth simplex and the birth simplex, you could actually have a smaller area from the length minimal or edge minimal optimization than the area minimal, which is sort of counterintuitive. So I guess if I had to choose one, I would choose a length minimal problem. But of course, it depends on your application.
And ignoring the integrality unless you want to be fancier. Okay.
Yeah.
Cool. Thank you.
Yeah, like, if you're probably that first application I proposed, the trabeculae problem, I think that one you'd really want to focus on an area minimal there. So it totally depends on your application.
So instead of a question, I actually have a comment. So I think there is one more reason why some good cycle representations matter from a theoretical point of view. That is, in one of the paper written by me, Facundo, and Osman Okutan, we proved that if we consider the Beatrice filtration of a Riemannian manifold, or even more generally, just an ANL space with a compatible metric, and if we consider, let's say, one persistent barcode, and some of the barcodes, some of the one-dimensional persistent barcodes came from the homology of the underlying space X. And actually, we were able to prove that those barcodes, which came from the underlying homology class of the underlying space, is upper bounded by L over 3, where L is the shortest length of the shortest cycle representation. And more general result actually hold not only for one-dimensional, more generally k-dimensional persistent barcodes is upper bounded by so-called k-dimensional generalized filling radius. And I think in that sense, those tight cycle representation or shortest length cycle representations are important in theoretical point of view.
Great. Yeah. Thanks for bringing that up.
Any other questions? Okay, if not, let me stop the recording, but we can discuss, continue discussion if anyone wants to.